My name is Mia, and this is the video write-up of Lab 2 for Physics 2211. Okay, so the objective of this was to analyze the motion of a projectile and compare experimental data with computational models. So we recorded a projectile's motion, extracted the data using Tracker, and then simulated it using GlowScript. The purpose was to compare the actual recording and the projectile motion to simulated projectile motion. And so what we used was a crumpled up piece of paper, and we threw it with a meter stick in the background of the video, and then we put it in Tracker. Or actually, I explained that like somewhere else. But it was about, oh, I switched the 2 and the G, whoopsies. Well, it was about 0.2 grams. So important principles and equations in this is that force equals mass times acceleration, and then the force of gravity is mass times 9.8. So when we're using Tracker, we converted the file to the right thing and uploaded it, and then I put all the data into Excel. So this is the checked out like the X versus time, or Y versus time, sorry. This is like X versus time, and then the actual table. Then we put in the computational model, so we put in the initial position as the vector, and then the velocity, which we calculated from like a final minus initial over 2. And then that should not say 9.7, that should say 9.8. But for this one, we had B as 0, because even when I changed B and ran the simulation, it didn't change noticeably. But so this was the position versus time, which matches up pretty well. This is the velocity, which also makes sense because it should remain constant. This is the position y versus time, which makes sense with the actual data that we found. Velocity of y versus time also makes sense because it slows down as it falls. And then this is also like the same trajectory position. So possible errors included like manual human error when I was actually tracking it in Tracker, and then obviously there's airflow and air resistance, which even when we changed the B value in the simulation didn't change the graphs or anything. And then also like camera angle distortions. And so the summary is real-world projectile motion is affected by air resistance, and the gravity-only model overshot the experimental data, and adding drag improved accuracy. So terminal velocity occurs when an object experiences zero net force due to gravity and air resistance. In the simulation, it doesn't show that, but the gravity and drag model suggests that velocity approaches a limit before hitting the ground. So to measure terminal velocity accurately, I could drop the object from a greater height and analyze how speed stabilizes over time. If I threw the object straight up with the same initial speed, the time to reach the ground would be longer than in my original experiment. This is because the object must first decelerate due to gravity, reach zero velocity at its peak, and then accelerate back down. With air resistance, the ascent takes even longer than the descent, making the total time even greater. In summary, my experiment confirmed that real-world projectile motion is affected by air resistance, and the gravity-only model predicted a longer range, while the gravity plus drag model matched the real-world trajectory. This shows how computational models can help refine our understanding of motion.